ladies and gentlemen. Thank you, David, for a nice introduction of mine, and thank you for coming. And today the topic of my workshop is graphs and collaboration networks. It's a hot topic now in our life, and I'm a specialist in game theory, and it is interesting how it's possible to apply game theory methods to analyze networks. And today I will speak mainly about social networks and collaboration networks. So that is short content, social networks, centrality measure, community detection, and maybe at the end, reputation model. So social networks, that is new phenomena in our life. And everybody of yours is related with it. In 1995, it was American portal Classmates. That it was the first social network. After that, it appears many social networks. 6 Degrees, LiveJournal, LinkedIn, that is for professionals, MySpace, Facebook, Twitter, YouTube, and others. That is the new style in our life, new challenges, new philosophy, and I'm sure that many of yours are in some social networks. I don't know which social network is applied in Hong Kong. Facebook maybe, yeah? Are you members of Facebook? Twitter, and what else? Instagram, yes, it's okay. And
Snapchat.
Oh, it's new for me. Maybe it's for young people. In Russia, we have Russian social networks, ВКонтакте and Одноклассники. No, Одноклассники is the same like Classmates. So it's difficult to explain why people organized social communities, but can you explain why it is interesting? Maybe some of yours explain why it is interesting for you to be in social network. Oh, you like communicate, change by movies, music, yes? So that is some kind of simple communications between people, because otherwise you need to visit your friend and speak with him. But now you can do it by distance. So that is simple and that's convenient for people to communicate. Social networks, the visualization of the social networks, that is graph. That is why we investigate social networks by the methods of graph theory. But how to construct the graph? That is the first step in social network analysis. The members of social networks, that is nodes in the graph. The links between nodes, that is some kind of communications, some matter of communications. It might be the number of information, for example, number of letters which are changing between nodes, between people. No, some later I explained how it's possible to construct the graph. So social networks, it is not mathematics. But when you construct the graph, after that you have some object for research. You understand me? So how to construct the graph from social network? For example, from Twitter. Anybody uses Twitter? Twitter, nobody. Okay, I explain you that. Huh? You use?
No, it's not.
Not popular.
Yes.
Facebook. I know that President of America uses Twitter. Russian Prime Minister Medvedev uses Twitter. That's it. Many politicians use it. I don't know why, but I'm not using Twitter. But anyway, I'm analyzing Twitter. So Twitter is a popular online social network. Twitter consists of tweets. Tweets, that is some announcements, some letters from one person to another. Tweets originally were restricted to 140 characters, but now the limit is 280 characters. In all languages except Japanese, Korean, and Chinese. Each tweet has the author, text, some text content, and author's residence. A retweet is a tweet in which one author refers to another. That is standard form of the tweet. So add name of another author. So, for example, the tweet can be attended the lecture together with Viktor Petrov, with somebody. So it means that you refer to another person. So you refer to that you know Viktor Petrov. And Viktor Petrov, in his tweet, in his letter, also can refer for you. You understand? So that is the possibility to draw a link between nodes. So you, Viktor Petrov, and there is a link between. So there is a graph. So graph nodes are the authors in the, for this social network. Edges correspond to retweets. If there exists a retweet of user J to I and vice versa, we may draw an edge between nodes I and J. If many letters between I and J, that is the weight of the link. No, that is standard graph of social network and collaboration network. So that is a graph of mathematical web portal MathNet.ru. That is in internet, you can show it. That is all Russian mathematicians, all Russian mathematicians. So nodes here, mathematicians. The link between two mathematicians, if they have joint paper. If have two papers, the weight is equal to. If three papers, the weight is 3. So in this graph, we have 800 mathematicians. Not only Russian, for example, David Young is one of these nodes. With number 48,135. That is your node here. Of course, it's huge graph. And how to analyze it? It's difficult. And some of links here, that is thick edges, but some of them only one paper between these authors. In this graph, there are some communities, some mathematical schools. And it is important to determine the schools here and to determine the correspondence between the schools. That is the aim of mathematics here. And so my first message is, you have social network or collaboration network, but after that you need to construct the graph. And that is first step in your research. You understand me? So that is the first step. After that, you will analyze it. But before it, you need to construct the network, the graph. For example, how to do it in any social network. I try to explain you. One of usual method here, that is vector space model. So what is it? So first of all, we have nodes, the office, the members of this social network. That is nodes in this social network. Each node is characterized by some documents, some letters, some correspondence. We construct the back of words. So that is all words mentioned in the text of all his correspondence. All words. For example, I like Julia, for example. Back of words. I like Julia. 3 words in the back. So in the correspondence, you determine all words, and after that that is your document, the document of the node. After that, you form D capital. That is the all words from all documents. Assume this big bag consists of K capital words. After that, for each word K from document DI, you calculate the frequency of occurrence in the document DI and denote it by WIK. So that is the frequency of word K in the document I. And after that, you form the vector. Vector DI, that is the characteristic of the node I, of the person I. That is the frequency of all words from big bag in the document DI. That is the vector. And for each document, you have vector. After that, it's mathematics. You have vectors, vector space. You have Euclidean vector space RK. And you have the vectors for each document in this space. After that, you can calculate, for example, the angle between vectors DI and DJ, and cosine. You calculate cosine between vectors DI and DJ like this way, and that is a measure of between these two vectors. So if the cosine is close to 0, it means that no relations between these vectors. That is different vectors. But if it's close to 1, it means that there is a big connection between these documents. And after that, you can calculate the graph. The graph that is people with documents, and the links here, that is relations between people in this graph. If cosine is close to 0, no any link. If it's close to 1, there is a link, strong link between people. So that is one way how to construct the graph corresponding to documents and to people in the social network. But there are some general used words like prepositions, copulas, etc., which are used in all documents. In this case, you recalculate the weight, the distance between documents using that you add here logarithm of here the ratio between n and that is number of documents, and here the number of documents which contain this often used word, and that is some modification of connection between nodes. Now, let us try to go to analysis of graphs which correspond to social network. Now, for example, we analyze Russian social network ВКонтакте. Now, for us, it is important to analyze the social community devoted to game theory. In game theory, we have 483 participants. So that is people from game theory which are interested in game theory, and they change by correspondence about game theory each other. But mainly that is students, Russian students, which send letter, oh, please help me how to find Nash equilibrium in matrix game. Or how, please inform me where I can find the information about dynamic games, for example. So that is usual correspondence between students. And for us it is important that we can calculate the graph, construct the graph, that is graph. So we have 483 participants here. And the weight, we have links between people. And the weight of the link, that is the number of common friends between participants. For example, we have with you 3 common friends. It means that the link between us, it will be 3. No, first view for this graph, what we can see? That we see that there is cluster here. No, there is some clusters here. And we see here there is cluster. You see that is the thick link. So many common friends between these people. So first view for the graph sent us some information about this graph. But for us it is important to find mathematical tools how to analyze it. Because otherwise, if you have graph 100,000 of nodes, it's impossible to only to view. We need to analyze it by mathematical methods. And it is important for all people. So after that, after we construct the graph, we need to say something. Who is the center of the graph? Who is important person in this graph? What are the communities? What people are interested in? What subjects people are interested? That is important for politicians, for journalists, for sociologists, for all people, for many people, for professional people. It is interesting, but you have only graph, and of course we need to introduce some mathematics, some mathematical methods how to analyze this graph. And the next, again, I show you the graph, mathematical graph, MatNet rule. That is graph of collaboration or co-authorship. And that is for Russian science, but the same can be made in Hong Kong for Hong Kong scientists, for many communities. That is maybe any professional graph. And now, what is possible mathematical tools for analyzing? First of all, we need to let us back to picture. So, for us, the first problem: how to find here the central nodes. What the nodes are important in this graph? For example, this node is important because this node is connected, this community, with this community. Some of nodes here are very important because they are in the center. But how to find important nodes in any graph? And the first characteristic was proposed by Freeman in 1977 in the journal Sociology, and he introduced to use the centrality, between centrality measure for each node in the graph. So centrality, between the centrality of the nodes I, he developed in this form. What is it? So let us calculate the number of shortest path between node S and node T. So we calculate all shortest path in the graph between two nodes, S and T. And after that, we calculate the general number of shortest paths between S and T, which follows through the link I. So firstly, we calculate the number of all shortest path between two nodes, all. But after that, we calculate only the shortest path which follows from S to T through the node I, which between them. And this ratio, we calculate for all possible S and T randomly appeared in the graph as T. So we randomly through the points the nodes S and T and calculate the ratio between shortest paths, general number of shortest paths and number of shortest paths which follow through the link I. The number of this possible randomly pair S and T, that is this number NB, so that is binomial coefficient n minus 1 over 2, and that is some normalization of this ratio that it was between 0 and 1. So it's characteristic between 0 and 1. And we calculate it for each node. And this node, this value is characterized, which characterized by this value, shows us the centrality of each node. So the importance of each person in social network. That is the first characteristic which was used by many people. But there is a disadvantage of this definition. And this graph, I show this graph, and please have a look for the node I. So in the definition of Freeman, we calculate only the shortest path. But you see here, shortest path from, for example, from 10 to 6, that is this shortest path. But never shortest path go through the node 1. So it means that centrality of node 1 is equal 0. So it's not good, because 0, number 1, it is important for this graph. For example, imagine that somebody destroyed this graph. No, for example, people divorced. After that, information will go through the node 1. So it is not 0. It is important node in this graph. But if you use the definition of Freeman is 0, it's nothing. It's not true. So what's to do? There are some possible ways here. We research in this area. Also, for example, we apply Kirchhoff model. So that is inverse Laplace matrix. No, the Kirchhoff law corresponds to electrical chain. So, so we can conclude, we can put current from here to any points. So we can put battery, electric battery here, no, some charge, and put the current from any point to another point. And the electricity, the current will be distributed in the electrical chain by like equilibrium in stable way. And after that we can calculate the potentials in each point. But today I will speak only about game theoretical methods which we apply for analysis of this model. So if we will apply game theory, in this case we need to construct some game. We propose to construct cooperative game. How to organize cooperative game related with graph? We have only graph and no any game. But anyway, it's very useful. The first who proposed to use game theory for a graph, that is Matthew Jackson. Maybe you know, very popular now book, Social Economical Networks, Matthew Jackson. And he proposed to use cooperative game theory for analysis of graph. And we use this approach here. So first of all, we need to determine the cooperative game. Cooperative game, that is characteristic function, and players. Players here, the nodes of these social networks, that are players. What is the characteristic function? We determine characteristic function in cooperative game theory, that is the payoff of any coalition in this game. Coalition in the game, that is any subset of a grand coalition. We determine the characteristic function by the following way. We have only graph. So, first of all, we introduce some parameter r, that is the value between 0 and 1. And we consider that every direct connection gives to coalition S the impact R. Any direct connection. So if you have link, the coalition has value R. That is the payoff R. But plus some additional rewards. So players, if in the coalition there is a path of length 2, this path gives to coalition S impact R square. A path of length 3 gives to coalition the impact R third, etc. So for any coalition S, we obtain the payoff of this coalition, the reward of this coalition, this polynomial. So that is the number of paths of the length of the number of direct paths, A2, that is the number of paths of the length 2, etc., etc. So this polynomial, that is the payoff of coalition S. So we determine the characteristic function. For example, if you have this graph, what is the payoff for this graph, for this grand coalition? So you see, we have 1, 2, 3, 4, 5 direct paths. We have 4, 2, 1, that is the path of the length 2, this path of the length 2, this path of the length 2, this path of the length 2, and this path of the length 2. So we have 5 paths of the length 2, etc. So we have this path of the length 3, etc. So we have the payoff for this graph the value of this graph coalition, that is this polynomial. So 5 direct paths, 5 paths of the length 2, etc. So this polynomial, that is the payoff of all of grand coalition. And for any coalition, we can calculate the characteristic function. So, for example, for coalition 1, 2, 4, 5, you see here 1, 2, 4, 5, what this coalition. If they organize this coalition, we have here 3 direct paths, 1, 2, 3 paths of the length 2, and that's all. So the payoff of this coalition is equal 3r plus 3r squared. And for any coalition, we calculate this characteristic function. After that, we can, in cooperative game, if we have characteristic function, after that we can calculate value, Shapley value. So we can distribute the payoff for the players, for all nodes. But Shapley value for graphs, for networks, that is Meyerson value. Shapley and Meyerson, that is Nobel Prize people in economics. So, that is the challenge for you. So if you will use the mathematics, you can be a Nobel Prize scientist. So that how we propose to find Meyerson value. So maybe I skip some slides, but idea is the following. So the Meyerson value or the Shapley value is determined by the following way. So and players, the permutation of all players are equally likely. So people can organize coalition like they want by a random way. And all permutations of all people are equally likely. And after that, we calculate the increment or the weight of each person in forming of new coalitions, and calculate the expected value. That is a Shapley value, but there is some specific for graph theory when there is relations between people. In this case, Shapley value presents Meyerson value. But for this case, Meyerson value can be calculated very easy, and this is theorem. But anyway, the Meyerson value can be calculated by through these stages. So on the stage 1, we calculate Meyerson value the following way. So, for example, 2 persons have direct connection. So this pair obtain payoff R. It means that each of players receives the payoff R2. And after that, we calculate the number of direct connection which belongs to player I. And we consider that each players which has direct connection, he received R over 2 payoff. And if we have the paths of the length 2, so it means that 3 nodes are connected. So in this case, the payoff R square must be distributed for 3 persons. So in this case, the payoff for player I, it must be the number of paths which follows from him of the length 2, and we distribute R square for 3 persons, no, etc. So, and the theorem suggests that that is Meyerson value. So, but to calculate it's very easy. Only the problem how to calculate the number of paths of the number of paths of the length k. No, it's not easy to calculate the paths, the direct paths, the number of direct paths, but it is difficult to calculate the number of paths of the length 2, 3, etc. in general graph. But anyway, there are some ways how to calculate it. One of them is that is, maybe this example I show you, how to calculate, for example, the weight, the weight for the player 2. So let us return back to graph. How to determine using this Meyerson value the value of player 2. So player 2 have 1, 2, 3 direct connection. So his Meyerson value is equal 3 r over 2. Also he has two connections, 1, 2 connection, 3 and 4. He has 4 connections of the length 2. So it will be 4 r square over 3. You see here 3 over 2r plus 4 r square over 3 plus etc. So it's easy to calculate Meyerson value using this approach. But what does it mean, Meyerson value? Meyerson value, it means that the grand coalition has some value, some profit. So, for example, 1. And when you calculate Meyerson value, that is the payoff which we distribute unit for everybody. And the person which obtain the payoff which is larger than others, that is important person. That is idea here. So that is centrality, game theoretic centrality in this approach. It's very effective. We can calculate Meyerson value, the number of paths of the different length using the generating function approach. I skipped this. That's mathematics, but that is can help us very much. Maybe this example. So, for example, here. So we have a graph, weighted graph. So the links between A and B is 1. The weight of link between A and C 1, but the link between B and C is 2. So it's twice bigger, twice more important than the links between other players. And here, so we have some graph. We can calculate, using this approach, we can calculate the characteristic function of this grand coalition. That is 9 direct paths here. You see here 2 plus 1 plus 1 plus 1 plus 1 plus 1 plus 2. So 9 direct connection, 4 connections of the length 2, and 4 connections of the length 3. And we can calculate the characteristic function for any coalition. And after that, we can calculate the Meyerson value for the player A. And after that, we can compare players between each other. And if we have numerical characteristic for the nodes, after that we can make something. So we can determine the important nodes in the graph. We can determine the stable coalitions in this graph. For example, we can introduce Nash stability for network partitioning. How we can do it? So you see here we can calculate the value, Myerson value, or that is centrality for each node. And after that, we can calculate, we can make network partitioning using this characteristic. How to do it? Now, for example, let us consider that a graph is divided for some coalitions, S1, etc., Sk. So it's not important. We can start from any coalition partitioning. So we divide graph for subgraphs. We have some communities. And after that, we, for example, consider coalition SL, any coalition from this partition. And let us consider a player I from this coalition. In cooperative game presented by this graph, subgraph, so that is the graph which restricted for coalition SL. So the nodes only from coalition SL. We find Myerson value for player I, that is Yi, no, like I show you in simple examples. And that is reward of player I in coalition SL. And what is the stable? What does it mean stable partition of the game? It means that now I'm in coalition SL. I like to change coalition. No, I'd like to be invited to another coalition. But if I move to coalition SK, in new cooperative game, we find the Myerson value Yi in new game, in another coalition. So I stayed in coalition SL. I had a payoff, a reward Yi. I moves to coalition SK. I received the payoff Yi. If it is not profitable for me, so if in previous coalition the payoff was larger, why I need to go to another coalition? So I will stay in my coalition. And if this partition exists, it means that it's Nash stable coalition partition. So it's very nice. So for each person it's not profitable to go outside. That is the idea how to make partitioning in the graph. Now, for example, here, you see that that is symmetrical graph, and if somebody asks you how to divide this graph for two stable coalitions, how to do it? No, of course, this coalition and this coalition, because all symmetric. But how to do it by mathematical way? What does it mean? Oh, now it's okay. No, why it goes down? You see that? It's no, it's. Okay. It works. So that is the idea for partitioning of graph for communities. So the partition N, that is, which consists of coalition S1, etc., Sk, this partition is Nash stable if for any player there is no incentive to move from her coalition to another. So if we find this stable partition, it's very nice, and we have dividing of the graph for some communities. And I show how to calculate the payoff of player I using the Meyerson value. For example, here, we like to prove why the partition A, B, C, D, E, F, that is stable partition. No, we calculate the Meyerson value for any node of these coalitions. For example, in this coalition A, B, C, that is coalition S1. So the payoff of this coalition is 4R. Why? No, because direct connection only 1, 2, plus 2. So 4 direct connection. So the payoff of this coalition 4R. The payoff of player I is equal R. No, that is his reward in this coalition. Imagine that this player like to join to this coalition. In this case, he joined, and we will have new coalition, A, D, E, F. In this coalition, we calculate the characteristic function on this coalition, that is 5R plus 2R square. We calculate the Meyerson value of player I in new coalition. His value is R square, using this approach which I showed you before, that is R over 2 plus 2R square over 3. And when it is profitable to join the coalition, if a new value is larger than previous value, so for R is larger than 3 over 4, in this case it's profitable to join. If not, it is not profitable. It means that if R less or equal than 3 over 4, in this case this partition S1, S2 will be Nash stable. So that is the idea. But there is another approach, very effective, which based on the so-called hedonic games. Hedonic games. Hedonic games were introduced in 2006, Bogomolny Jackson, and the idea is the following. In hedonic games, the payoff of each person depends only on his coalition. So, in hedonic games, the payoff of each player can be determined via preference relation. No, I showed you the approach. Assume that the set of players is divided into K coalitions, S1, etc., Sk. Denote SPI, that is coalition which belongs to partition P, such that the player I belongs to Sk. So SPI means the coalition which contains the player I. And after that, determine the preferences for player I. Player I preferences represented by a complete reflexive and transitive binary relations like this over the set S. So for us it is important to determine which coalition is more preferable for player I. So player I prefer coalition S1 than S2 if the sum of these preferences values in coalition S1 larger than the sum of preferences in coalition S2. That is definition of hedonic games. And it's very useful. Some later I explain you why. And because this relation is symmetric, in this case we will write Vij only, no, like here. So Vij is equal Vji, and we will denote it like a Vij for any players from the set N. And now definition, important for us. Network partition P is Nash stable if player I prefer his belonging to coalition from partition P, then if he joined to any coalition from this partition. So now he belongs to some coalition. For him it is not profitable to join to any coalition because for him it is more profitable to stay in his coalition. So no, in Nash stable partition, no players who want to leave from her coalition. And this game is effective because in this game we have potential. Bogomolny-Jackson proved the theorem, not so complicated, but anyway, that the potential in this game is equal the sum of all preferences relations. So you see here the first sum, that is sum through the coalitions from 1 to k capital, and here for all ij belonging to coalition sk of the functions of the preferences Vij. And the Nash equilibrium we can find if we find the maximum of this potential function. That is the idea, general idea. But now we apply how to do it here for graphs. No, that is the theorem of Bogomolny-Jackson. So if players' preferences are additively separable and symmetric like here, then coalition partition given a local maximum of potential function is Nash stable partition. So we will use it for real applications. So let us determine preferences Vij by the following way. So imagine that the graph is divided for some communities, for subgraphs. We introduced function Vij the following way. If the edge, the link, belongs to graph, in this case, Vij is equal unit minus alpha, alpha some parameter. And if no link between I and j, that is minus alpha. And if I is equal to j, that is 0. So that is preference function. After that, for any partition, we can calculate potential in this form. So MSK, that is number of edges of links in subgraph SK, in community SK. NSK, that is number of nodes in this graph. And alpha is parameter. So potential has this simple form. And after that, we can introduce the algorithm how to calculate the how to clustering the graph. Introduce special decomposition of networks into cliques. First, let us find the maximal clique. Clique is a fully connected graph, so all nodes are connected between each other. So first we construct we find the maximal clique S1 in the network, and after that we skip all nodes from all nodes of clique S1 from graph G, and consider the new network G1. In G1, we find again maximum clique S2, etc., and we continue this procedure until empty graph. Call this partition like a sequential decomposition of network into maximal cliques. And next proposition: if alpha is 0, the grand coalition N gives the maximum of potential A. If alpha is close to 1, the maximum of potential corresponds to network sequential decomposition into maximal cliques. Now, in example I show you, you see here 4 cliques. So 4 cliques. If for different alpha, we will have different decomposition of this graph for the subgraphs. Maybe, no, I show you that how we calculate potential here. It's not so complicated, but maybe it is important this table. So you see that for different alpha, we have different decompositions. So if alpha is small, that is the optimal partition, that is grand coalition. If alpha is between these parameters, in this case, the optimal partition is G1 and other players. So if alpha is small, in this case, G1, and after that, other nodes organized joint coalition. If alpha between 1/77, 1/15, in this case, the optimal partition G1, G4, and G2, G3 joining. And if alpha is close to 1, that is the decomposition in 2 cliques. So if alpha is close to 1, in this case, we divide this graph for stable partition. It will be 4 coalitions. No, it's natural here. No, we can do it for weighted graph and for unweighted graph. No, here what it will be. Here we calculate. Here, if we use potential approach, in this case we will have, if alpha is less than 1/9, in this grand coalition is stable. If alpha is larger than 1/9, in this case we will have 2 stable coalitions. And very popular in this area, Zakhary-Karate club network. So Zakhary in 1977 observed 34 members of Karate club in period of 2 years. And it was some disagreement between administrator of this club and club instructor, and new clubs appeared, one of them with instructor that is node 1, and another with administrator number 44. So 15 people here and 19 people here. So that is a real story. So people friendly connected each other, but it was disagreement between 2 persons, and this club divided for 2 parts. That is a real story. But how to do it by mathematical way? Girvan and Newman, this work is very popular in this area. They use the hierarchic approach with dendrograms. Another story, but it's a very complicated algorithm. They divide this network into two groups using the hierarchical clustering tree. They show that this graph split corresponds almost perfectly the real story. Only one node, node 3, is classified incorrectly. So this node belongs to in real story to this cluster, but in the algorithm of Girvan-Newman, it belongs to here. So we use hedonic game approach here, and we obtained for different alpha different partitions. So if alpha is equal more or equal than 10 over 289, the Nash stable partition is like in the Hari case, and the node 3 belongs to the right coalition. So you see that for some parameters alpha, this approach gives real story, corresponds to real story. Also, in this area is very popular modularity. Modularity was also proposed and used by Newman and Girvan. But in our case, we can use it to determine the preferences relation for hedonic game. What does it mean, modularity? Modularity, that is the difference between random graph and real graph. So imagine that we construct the random graph. So we know that in this graph we have m links, and in each node we can calculate the number of links which follow from this node. So di, that is, we call it like a degree of node I, and dj, that is the degree of node j. So imagine that from each node randomly we put the di links randomly. From each node we randomly we send some links. We send some half links, and if two half links meet together, in this case we have link between two nodes, and the probability to join two nodes I and j is equal di times dj divided for 2m. 2m, that is general number of half links. And aij, that is the real number of links between nodes I and j. So this difference corresponds to difference between random graph and real graph. And of course we'd like to maximize this difference for all possible nodes I and j. And if to determine the preferences by this way, in this case we can use the same approach with potentials, but with new preference relations. So we did it for this graph, and for gamma is equal 1 and beta ij. That is only parameters of this algorithm. We can determine these parameters as we want. And for example, for these parameters, the partition for two coalitions, ABC and EDF, that is unique Nash stable coalition here. Now, for example, we divide MATNet rule, partitioning. For the moment, we can't to divide all graph of MATNet rule. MATNet rule, it's about 100 of thousands of mathematicians, Russian mathematicians. But half of them, we do it using the Monte Carlo method. So approximately 50,000 of nodes, this graph, we can divide for stable Nash coalitions. Imagine that this algorithm is very useful. It's impossible to apply Girvan-Newman algorithm using the clustering tree. It's impossible for this big graph. But our approach is very useful, and using Monte Carlo method, we can divide any graph for 100. I'm sure that we can do it maybe this year to divide graph from 100,000 of nodes. We can divide for stable coalitions. Now, for example, here for some of fragments of this MATNet rule graph, we can do it by this way. So you see that is simplified graph of MATNet rule. We divided it for these 9 coalitions. And this coalition, when we compare this partition with real situation, we have good coalitions. For example, probability theory with, Kolmogorov is founder of Russian probabilistic school. Kolmogorov is here, and that is a school of probability theory and random processes. Gelfand school is here. That is Pontryagin school is here. So it's interesting to compare real partition with partition which can be doing by mathematical way, formal way. No, I don't know. 5 minutes. No, maybe I shortly. Finally, some words about reputation. So in social networks, we have nodes, that is people, relation between people, that is links between people. We can organize, on the first step, we organized graph. So graph is determined by adjacency matrix, so that is big matrix. So 100 of thousands columns and 100 of thousands of rows. So in computer we have this big graph. After that we use some approach. For example, we can use hedonic games or Myers and value. We divide this graph for some coalitions. But also it is important the relations between people, because some people are doing by correct way, other people not correct way. So for example, if we change by music, so I sent you music, but you don't send me music. It's not good. So in this case, it's good to introduce some reputation of people in social network. How to do reputation here? No, one of possible ways that is model based on the Markov chains. How to determine the reputation? So we have some social network. We have players. They are not players, but we call the members of networks like players. We have graph of network, and let us introduce the reputation matrix. Rij. That is the rate of reputation. We consider that R, that is stochastic matrix. So the sum of Rij in J is equal 1. So that is stochastic matrix. And imagine that x of t, that is vector of decisions of each person, 1 or 2. So, for example, for the moment, we are social network. For example, now we need to decide to go to the movie or not. Some of them say, "Oh, I like to go to the movie. I like to go. No, I don't like. I like." So we have some vector of solutions, original solutions, to go or to not to go to the movie. But after that, we'd like to connect each other, and we discuss it, to go or to go, to visit or not to visit the movie. And it means that for the next step, we change solution. So everybody changed his opinion, original opinion. And they change it by this way. We multiply matrix R for previous solution. And after that, we have this dynamic. And we have this equation. So in moment t, our opinion is changed using the reputation matrix and original opinion. But from ergodic Markov theorem, we know that when we multiply, when t is tending to infinity, we have matrix R infinity. But from ergodic Markov theorem, R infinity consists of the same probability vectors. So this matrix consists of identical probability vectors, which can be easily calculated. In this case, the final solution, that is consensus, x capital, and consensus is calculated by this way. So after discussion, we follow to one consensus, to go or not to go to the movie. So that is good model for modeling of reputation. And now it's very useful in this theory. No, using this approach, we can determine the information fighting between people, etc. Maybe I stop in this moment.